Okay, assalamu alaikum everyone. Let's wait for a couple of minutes for some other guys to show up and then we'll start, inshallah. Assalamu alaikum, Shah. How are you? You look fresh, mashallah. Thank you very much. Okay, so what we're going to do in the first half is, so far we have looked at the architecture of GPT-3. We're going to look at some more architectures like Llama and Mistral. And I'm going to just take you through a few papers of these architectures, just to show you that now you guys are in a position to read these papers, because there is nothing in those papers which you don't understand. For example, if you pick up, let's say, DeepSeek paper, version 3, you can read it now. You will understand all the details, except for reinforcement learning with human feedback, which we will do over the next 2 days. And then my job is essentially done. If you can pick up any paper of a large language model and you can read it and understand it, then that's it. That's a very good outcome for this course, because then you can just take the straight of the art paper, read it and understand it, and then do your own improvements on top of it.
Why is Llama so popular in
Because it's open source. Because it's open source. You have the weights, you have the architecture, you have everything available. But Mistral and Llama, I think Llama is probably better than Mistral. Mistral had some very nice ideas, which are now standard. For example, Mistral had mixture of experts, which is now standard. DeepSeek version 3 has a mixture of experts as well. But Llama, I think, was the first. It was good, and because it's from Meta, they have, of course, it's a much stronger company than smaller. Mistral is, I think, a French company, European company. So Llama has huge potential. I think like Meta will keep on putting out these good models, and they would be foundation for other models. Of course, now I have a feeling that the Chinese company might be better in open source domain than American companies. For example, like there are many companies, not just one or two in China, who have excellent large language models. And DeepSeek is not an exception. It's just that we don't get to hear much about them. We don't know a lot about them. But Chinese companies might be taking the lead in the open source large language models. But Llama was the first one. It was the first one in public open source. People were first to jump on it, so that's why it's quite popular. And it had some good ideas as well. We'll see some of these today.
Maybe it's because they launched it very early.
That's what I mean.
They take the
market share. Yes, yeah. Because
Gemma and Quinn is also good.
Yeah. Quinn is from a Chinese company, right? Quinn.
Yes.
Yeah.
Alibaba.
So what time is Juma exactly? What time is Juma exactly? Can we finish at 11:45 and reach Juma, or 11:40? 45 is good.
It's 12.
12?
12:03.
12:03. Okay. So we'll finish 11:45. Just prompt me. We'll go pray Juma together somewhere and then come back. We start around 1. Okay.
Maybe we start at 12:45.
12:45 we started yesterday, so I'll be here 12:45. Everyone is there, will start. If not, we'll start 1. Okay, so can somebody drop a message on the group that we are starting, and we will start? Okay, so what we have seen so far is standard transformer architecture in GPT-3. Okay, and essentially this picture, this is from, this picture is from the 2017 paper of Attention is All You Need. But GPT-3 is, or GPT-based architecture is essentially this part. Okay, they have, because this is the encoder, this is the decoder. Remember, GPT-3 and large language models in general are decoder only model. They have just this part. Essentially, we have seen what is the input embedding, what is the positional embedding, what is multi-head attention, what is add and norm. By the way, what is add and norm? Normalization and adding. And normalization is just you take an embedding, subtract the mean from it, divided by the variance of that. Okay, make an embedding zero mean unit variance. That's the operation. I will talk a little bit more about it. Then the feed forward network, addition and norm, a linear layer, and a softmax. This part is repeated n times. So for example, in GPT-3 case, it was repeated 96 times. So we understand these architectures. Okay, now let's look at the architecture of Llama. Okay, there are a few improvements, a few changes on architectural side. And by the way, I'll show it to you in the papers as well. The changes in architecture part of these models would typically be like half a page. Because as I mentioned yesterday, architectural changes are not what drive progress. What drives progress is the size of the model and the data that you are using. So more effort is being put into making these larger scale, like make them bigger, go from a couple billion parameters to 175 billion to 1 trillion and so on. Okay, and of course, also training them better, making them fast at inference time. So we'll look at some of these topics. So this is the architecture of Llama. Okay, so what you see is the major changes is the first thing is that they have something called RMS now. Okay, root mean square now. Okay, then they don't have any positional embedding here. Rather, they have something called positional encoding for query and key, but not for value. Okay, next you see is that they have something called SWIGLU. Okay, SWIGLU is basically a modification on the traditional feed forward network. Okay, they just change the activation functions. So let's look at each of these changes in detail. So the first thing is a typical normalization layer in a transformer would take an embedding, okay, subtract the mean of the embedding from it, okay, divided by the variance of the embedding. That would be embedding normalized. That's typical normalization in a transformer architecture. So basically, if you have an embedding for a word which had value, let's say 1, 0, minus 1, and 0, okay, you will take the mean of it, which is 0, and you will take the variance of it, which is 2 divided by its n minus 1. Typically, when you take the mean, it's number of elements divided by n minus 1. But to make my life easy, I'll take it as n, take it 4. Okay, this is 0.5. So when you normalize it, this would become 1 minus 0. So 0 divided by this 2, 0 minus 2, 0. Okay, this is now normalized. It has 0 mean and unit variance. Okay. In this case, I took the data already too well, but if you take large numbers, you would see that it would make it well posed. Essentially, the core idea is that if we assume that these elements of this embeddings are coming from some normal distribution, so EI is coming from some normal distribution with some mean and some variance, then this operation, subtracting the mean and divided by the variance, would convert it into 0 mean and unit variance. That's the idea. And this, by the way, does not change anything in terms of learning because it does not have learnable parameters. But what it makes an improvement in is the training. So it makes training easier. Okay, it's just make the problem well posed. The number do not grow too much, so you can essentially train things well. Okay, everybody's with me. Okay, another intuition for this is that if you don't do normalizations, So what is a neural network, or what is any deep architecture? Essentially, it's a series of layers, right? You have layer 1, you have layer 2, layer 3, and so on. You can have some layer n. These can be attention layers, fully connected layers, convolutional layers, any layers, don't care. Okay? But if things are not normalized, then what can happen is that the backpropagation through the loss can produce very large changes in early layers, okay, or in some of the layers. Let's say that the backpropagation was such that this changed a lot. When this changes a lot, all the input that goes to the next layer, it changes completely. It changes into things which your network has not seen. So training become very unstable. It's basically you're jumping from one place to another. Essentially, training is stable when you're making small incremental changes. Okay, then you can learn much better. So I'll give you an example. Let's say you're making a recipe. You're making a soup which has 10 ingredients, and let's say the soup does not turn out to be good. Okay, now I'm hoping that you guys would agree with me that a better approach to fixing this soup would be now you start changing a few items. If you start changing everything randomly, it'd be very difficult to find where the mistake was. So you start looking at it systematically. You say, okay, let me decrease the salt in it first and see if it works. Okay, let me add some more spices. Let me add some za'atar or things like that, whatever. So incremental changes work. That's basically the rough intuition of normalization. That normalization prevents the network from jumping too crazy here and there, and try to make it slightly well posed, which makes training more easy. Everybody's with me? So in the RMS norm, by the way, was not introduced in Lava paper, they just used it. The idea of RMS norm is that there are two things that we are doing in normalization. So you are taking an embedding, you are subtracting the mean of the embedding from it, and you are dividing by the variance of the embedding. Okay, so there is a part of renormalization. And there is also a part of recentering. So you will have a distribution like this with some mean and some variance. What you are doing is you are recentering it, you are bringing it to zero mean, okay, and you are renormalizing it to have a variance of 1. So the idea of RMS norm is that it's the renormalizing which is very important. Recentering is not that important. Okay, so what they do is they say that we want to renormalize the data. We don't want to necessarily recenter. Okay, but remember, for renormalizing it, we are using variance. Okay, and variance would typically, to calculate the variance, you would require the mean. Okay, right? Because to calculate the variance, you will take the square of a number, square of the entity, subtract the square of the mean from it, add all of them up, divided by n minus 1, right? So the question is, what can we do in this case? If you have to calculate the mean anywhere, then we will just recenter it as well. The whole idea of not using the recentering would be that it saves you some computation. So what can you suggest we use for renormalizing? That can renormalize things, but does not depend on the mean. Just the squares. There's a square, mean square, something like RMS root mean square. So what they do is they say that we will create the mean square, okay, which is, by the way, you guys should have corrected. We don't divide it by the variance, we divide it by the standard deviation, the square root of the variance. That's why this thing was a bit weird. Anyways, the mean square would be, you go over each component of your embedding and you take its square, okay, and then divide it by the number of the component that you have in it. This is mean square. A root mean square would be square root. So you take this quantity, and now your modified embedding is EI divided by RMS. That's the normalization that they use. That's the idea of RMS normalization. Another thing that you would note is that they have moved the RMS norm before the layers. In typical architecture, we had the normalization after the multi-head attention and after the feed-forward network. What they do is they move it before. Again, the idea is that input to the layers, if it is well structured, if it's well contained in some range, then the outputs automatically would be better. Okay? So they normalize the input embeddings to the attention layer, and then they also normalize the input to the feed forward layer and output of the feed forward. So just more normalization typically would tend out to have better results. Any questions in this part? Everybody's with me? Okay, so what Llama has is RMS normalization, which is nothing fancy, just a different type of normalization, which is interested in rescaling, but not necessarily interested in recentering. Okay, let's come to the second part, which is this positional embedding. And what is this rotary positional embedding? So what we have done so far, what we have studied so far in transformer architecture, again, this positional embedding idea came from the original attention is all you need paper. So in attention is all you need. What the author suggested was that when we have the input embedding, okay, the embedding for token 1, embedding for token 2, all the way till embedding for some context length, what we do is we add fixed positional embedding with it. So we have a positional embedding for position 1, positional embedding for position 2, all the way till positional embedding for position C. These are fixed. We don't learn them. We fixed them in attention is all you need paper. Okay, and we just added to tell the transformer architecture where the word is coming from. Because remember, attention is an operation on sets. It does not take any order. Okay, a word can be the first word in a sentence, and attention with the third word would be the same. So same. The car is good. The car runs. So this car and this car would have the same attention with this term. Okay, because remember, the attention only depends on the value of the embedding. Attention mechanism has no way of finding out where this word is coming from in this sentence, which is not good because language has structure. Order matters in language, right? So somehow we need to capture this order. And for that, we added a fixed positional embedding vector to our embeddings. Okay. And what they use in the paper is basically sines and cosines. So they have something like sine of position divided by some fixed number. I think it's 10,000 for them to the I by D. Okay. Where I is the component of the embedding that you are working with. Essentially, what you want is these vectors to be orthogonal to each other, okay, and unique. Basically, if each position is represented by a unique vector, which is not a linear combination of another vector, then the network will, looking at this vector, the network would be able to tell that this word is coming from position 3, this word is coming from position 5, this word is coming from position 7. That's what we did. Okay, so these were global positional embeddings. They were added at the input layer, and because of the skip connection, of course, they were added at all the layers as well. And that's how we knew where the word was coming from. So Llama said, let's use a smarter idea. The idea in Llama is that we are not essentially interested in the absolute position of a word in a sentence. Okay, what matters is what is the relative position of a word with respect to another word. Okay, so I'll give you an example. I'll say that I am not happy. Okay, and I am happy, not sad. Okay, now in this case, what is important between happy and not is their relative position to each other. Okay, in this case, not is a token before happy. In this case, not is a token after happy. And in the context of sentence, it would change their meaning. Okay, now, if I have 15 other sentences before it, it does not change the impact that not and happy have with each other. Okay, so its position can be 30th token and 31st token in a sentence, or it can be 39 token and 40th token in a sentence, or it can be first token or second token in sentences. What is important is their relative position. Everybody's with me? Okay, that's what we want to capture in this embedding that they use in Llama. It's called RO, relative positional embedding. So the question is, do you know of some transformation of embedding where we can capture essentially what is the distance between the two tokens? Can you guys think of something like that? Hmm? No, but norm has no notion of position, right? So remember, you distance how? Okay, so you calculate the distance, but then how do you encode it in embedding? Because you have to pass this information. I can find the difference. I know that the difference between not and happy is 1. Okay. So the way they do it is they say that they would use something called rotary embeddings. And I will take a simple example in 2D. Okay. So in 2D, they would say that I have an embedding which is cosine of theta minus sine of theta, sine of theta, and cosine of theta. Okay. If you take an embedding, E1, E2, and do the transformation, let's say that originally the embedding was this. What this transformation would do is it would rotate it by theta. Okay. If you do this transformation again, it would rotate it by an amount, theta 2. Okay. So now you can see that I have a transformation which tells me how much this embedding is rotated. So if for each position, I have an embedding which is cosine of m theta 1 minus sine of m theta 1, sine of m, sine of m theta 2, sine of m theta 1, I'm sorry. Then this would, if the token is at m equal to 2 position, it would move it by 2 theta 1. If the word is at m equal to 4 position, it would remove it by 4 theta 1, and so on. So the relative rotation of the vector is equal to the position of the word in the sentence. Okay, so if every word is rotated equal to where it is in the sentence, then I would be able to tell that, hey, this one is at 4th position, this one is at 5th position, this one is at 3rd position. That's basically the idea. Okay, yeah. Eigenvalues of what?
These two matrices.
No, but to what effect? Like, why would you want to use eigenvalues? Because remember, what do I want to do? I want to have an operation. I want to have some sort of positional embeddings, with which I can capture the relative distance of two words in a sentence. Okay. So if I want to use eigenvalues should be able to capture it for me. Eigenvalues first, eigenvalues of which matrix?
It changes from the matrix 1 to the matrix 2. Isn't this eigenvalues?
No. So you have to have an eigenvalue first. Sorry, you have to have a matrix first to calculate its eigenvalues. There should be a reason to find its eigenvalues, right? Eigenvalues are basically just telling you what are the direction of changes of or transformation of a matrix where the output vector is in the direction of the input vector, or just scaled up or scaled down. Okay. So this is basically what they use, where m is basically the position of the word in the sentence. Okay, so when you take the query key product, it will have a component in it, which would have m minus n theta 1. Basically, essentially just telling it what is the relative distance between the two words. And another good thing of this is that if you look at the relative upper bound on this relative position embedding, you see that the impact of words decay as we go further and further from the word, which is also a good property to have. Words in immediate context would be very important. Word in previous contexts would become lesser and lesser important. Some of them can be important, but the probability of them becoming important would become less and less. So this is also a desirable property that we have in that. Okay. Now the challenge that I have for you is that I can do this rotation in 2D. Okay. I can tell you that I have the sine of m theta 1 minus sine of m theta 1, sine of m theta 1, sine of m theta 1. This would take a two-dimensional embedding and rotate it. But embeddings we saw are 12,228 dimension, 512 dimension, and so on. These are very high dimensional embedding. So what can we do in this case? How can we rotate the words in these very large embedding space? I'm sorry? Okay, so what the smart idea that they use is they just broke it down into set of two embeddings and rotated them. So the first two embeddings would be rotated like this. The next two embeddings would be rotated like this. And so on. Okay. Yes, so essentially what you do is you are saying that you take the embedding vector E1, E2, E3, E4, 5, 6, and all the way till, let's say, D minus 1, ED. So these two, you rotate them by m theta 1. These two, you rotate them by m theta 2. These two, you rotate them by m theta 3. These two, you rotate them with m theta d by 2. Okay? Rather surprisingly, it's very easy to calculate. I'll tell you why. Because this is a sparse matrix, right? So if you do this calculation, essentially, each one of this would be E1 out would be cosine of E1 minus sine of E2. No, because it's a simple transformation. Just bear with me 1 second, you will see. So E2 would be sine of E1 plus cos of E2. Okay, similarly, you do it for E3 out and E4 out. So E3 out would be E3 cosine of E3 minus sine of E4. E4 out would be sine of E3 plus cosine of E4. So now you can see that this, essentially, let me do it the other way. So if I collect the sines, cosines from all of these, this one would be E1 tilde would be cosine of E1, E2 tilde would be cosine of E2, E3 tilde would be cosine of E3, and E4 tilde would be cosine of E4. Okay, now let me collect the sines of all the terms. So this would be sine of E2 plus sine of E1 minus sine of E3 plus sine of E4 and E3. Okay, so now you can see this is just the embedding vector multiplied with cosine. This is the embedding vector, but first and second element flipped, third and fourth element flipped, fifth and sixth element flipped, and multiplied with sine with the power minus I to the power I, minus 1 to the power I. Okay, so it's a very simple calculation that we can do quite efficiently. Okay, so once you calculate the output embedding, Rotating it a second time again is the same calculation. Okay, so the product of two transformation is essentially this operation twice. So you can do it fairly efficiently. It just takes 2D multiplications. Okay. So that's basically the idea of rope. Okay, so now we can attend to a word which would look at the query and key, but also look at the relative distance of the two words, how far away they are compared to each other. Okay, and the good thing is that, see, if you wanted to hard code the distance, it's not a trivially easy task because you would have to write the distance of each word from each word. Okay, so it's not just one number. You cannot say that, hey, this is a distance 1, this is a distance 2, this is a distance 2, because it's from each word to each word. But in this case, now it's effectively done. Okay, with just by adding these, doing this transformation, these rotary embedding transformation, you can encode the relative position of all the words relative to each other inside this embedding. Okay, so smart idea. The other thing is that because we are capturing the relative position of the words with respect to each other, their effect would be captured in this key query multiplication. We don't need to modify value vector in any way. So remember, in our original paper, we were adding the position to the embedding. Because of that, all the key query value, all three matrix vectors was changing, right? Because if you change the original embedding, then if you do a linear transformation of it, of course, it would be different from when you had unchanged embedding. But in this case, the value vector is not changed. The effect of this value vector would be captured by the interaction between query and key. Okay, this is a smart idea. Okay, so value vector in the context of the sentence, it would remain the same. Okay, how much it affects other part of the sentence would depend on the relative distance between these words, and which is captured by the rotary embedding of the query and key. Okay, so that's the second book. Okay, so everybody is with me. Everybody understands this rotary embedding for query and key. Okay, a smart, neat idea, nothing too mathematically complex, as is the case with large language models. Nothing is too mathematically complex, with the exception of reinforcement learning with human feedback, which we would look at in the afternoon. Okay, so let's talk a little bit about the feed-forward network. What is this Swiglu network? Let me open a summary of it somewhere. Okay, so a typical transformer has this as a fully connected neural network. So you have a linear transformation, okay? Then you take a ReLU of it, then you do another linear transformation of it. Okay, so essentially what you would do is you would have, let me just write it. So a typical feed-forward network, a neural network would have max of 0 of xw plus b. Okay, then you take this, then you do, we call it w1 b1, w2 plus b2, and max of this and 0. This is a typical feed-forward neural network. What they suggest is to use Swiglu. Yeah, Swiglu is slightly different. So it has a swish function. I will explain what swish function is. Then it has an element product with x, which is linear transform. And then you do the second layer, which is W2. Okay. So let's see what swish is. So swish is basically a sigmoid multiplied with the input of the sigmoid. Okay. You have a parameter beta here with which you can see how sharp, you can adjust how sharp this sigmoid is. Typically in Swiglu, we use beta equal to 1, which is called sigmoid linear unit, CLU. Okay, and CLU is essentially x divided by 1 plus exponent minus x. Okay, why is this good? Because it looks like this. Remember if we use ReLU, ReLU is essentially just It is 0. ReLU is essentially just this and a straight line. Okay. But CLU has a little bit of dip below. It's slightly more smooth. Its derivatives are well defined. Okay. So rather than ReLU, they use CLU. Okay. Which is this part. Then they have this element-wise product of each output of this linear activation with X time V. V again is a learnable parameter. Okay, and W2 is the output of the, the weights of the second layer. Okay, so they tried it, and what they saw is that it performs slightly better. They have this funny, and this is from the original paper of Swiglu. Okay, they have this funny quote, but slightly meaningful as well. So we offer no explanation as to why these architectures seem to work. We attribute these successes, we attribute their success as all else to divine benevolence. Okay, so we just say, Alhamdulillah, it works. We don't know why it works. Okay, and I will take the same approach. I'll just say that Swiglu is better. I'm not going to try to explain why it's better. Okay. You can, of course, make the case that it's better because it has more learnable parameters. It has this V. But what they do is when they're testing, they try to decrease the number of parameters in Swiglu network so that the overall number of parameters in both networks is equal. Okay. Even then, Swiglu works a little bit better. Okay. This is another change. Now the major change, which is which I did not cover, is the grouped query multi-query attention. Okay, the group multi-query attention and KV cache. So this is an important topic. This is in fact one of the major contribution of DeepSeek version 3 is a smarter way of doing KV caching and multi-query attention. So let me explain what the challenge is. Okay, I'll give you the challenge and the solution. When we come back, we'll look at it. So the challenge is at training time, if you have a transformer, okay, we want to train it. Let's say you have a sentence. Today is Friday. Okay, and you want to use this in training. How would you use it in training? You would have start of sentence token. You would have today. You would have is. You would have Friday. The corresponding outputs for this would be today is Friday. End of sentence. Right? So you take the inputs, you take the sentence, add a start of sentence token to it. You take the sentence, add the end of token to it, put it as input output of a transformer, and alas, you are set, you can train. Okay. Now, one other thing that you would do is that when you calculate the attentions, you would put a causal mask. Okay. You will make the top part of the attention 0 because a query cannot talk to future tokens. It can only talk to past tokens. But all of it, like the effect of D tokens, or tokens, let me use something else, C tokens in context. All C tokens in context can talk to all C in context in a single operation. Okay, we did it yesterday. We created this big Q matrix, the big K matrix, the big V matrix, and the big O matrix, and all of it super parallelizable, and you can do it really, really fast. At training time, everything is good. Okay, but at test time, it's not the case. Okay, at test time, let's say if I give you a prompt, and the prompt is write an essay on KV cache. Okay, this will go as input to your transformer. Okay, out will come a single token. Okay, maybe the first token is KV. Then you add KV here. You take this, you give it input to your sentence. outcome, the next word, which is maybe cash. Okay, you add cash here, you take this as input to the sentence, give it here, outcomes kb cash is. Now you're doing token by token. Okay, so this token by token calculation can be slow. Okay, and if it's slow, then it kills the entire purpose of language model. Remember, the OpenAI and Google and Meta, they're not spending money on LLM because LLM are easy to train. They're spending money on LLMs because LLMs, we can use it to talk to it, to produce text from it. If, let's say, I ask it to write an essay and I have to wait 3 hours for it to complete the essay, then the whole point of doing this is gone. Okay. So this is a whole area of engineering where we want to make transformer-based architecture faster at inference. Okay, that's where multi-query attention came in. That's where grouped query attention came in. These are concepts of Llama. That's where KV cache came in, which is also a concept of Llama. This is where sliding window attention came in, which is a concept in Mistral. And that's where I think it's called latent, some sort of latent space compression of KV cache, which came in DeepSeek version 3. So we need to look at a little bit of these design and architectural change over the past 3-4 years to make inference fast. The whole idea is to make inference fast. Okay, you can have a very good trained thing, but if it's very slow at inference, it's useless. So we need to make things faster at inference. Okay, when we come back, we'll see how it's done. Okay, thank you very much. Somebody has to give me a right to ask. So we'll try to start at 12:45, inshallah. Okay, maximum 1, but hopefully we'll start at 12:45. I'm sorry. No, I'll go. Let me do it there.
No.
يعني إذا كان شيء أصعب أكيد يعني الدكتور فيها درجات أكثر يعني.
يعني الدكتور بشوف احنا نزلنا شيء على يعني
هو بشكل عام مبدئيا قال لي بحاول أعطي اللابتوب اللي follow the structure بشكل عام follow the requirements. بس الإكسترا ستاف يعني قال لي ما أحس إنه داعي يسوي. إيه بس يسوي هذا المهم.
المفروض نشيلها من الست ما يقدر يسويها. أنا شفت من نسوي السلام والشيء بعدين شغل ونسويها في بصير نسوي فيها مرتين بس.
الواجب الأول كان لأجله
الواجب الثاني
الواجب الثاني هو الثاني وزي درجات معقولة الدكتور بس قال إنه راح ممكن يسوي له أبجريد إنه يكون له تحديد بشكل عام بس درجات أساسية بس لسه ما في صراحة يعني بس كل تخبط في ناحية الدرجات كذا يعني زي ما قلت لكم اللي تسوي ستراكشر نفس اللي لو فاتوا تسوي ريكوايرمنتس كذا مرة طيب إن شاء الله
بعدين ناخذ الشعر هذا اللي لقيناه اسمه الشاعر هذا نسوي جنريشن بما أن الستايل حقه. طيب كيف نسوي على الستايل حقه يعني نخلي يصير تكست هو شاعر حقه هذه طريقة تمام. عادي الفوكابلري نسويها كاركتر ليفل.
موضوع السؤال شديد.
لا ما عملنا بس قال create vocabulary based on the clean deficit.
إيه هو موضوع عندك مجال تسوي البرنامج هذا.
صح بس هذه أسئلة خلصتها بشكل عام. شاعر يأتي من الثلاثين Yeah, the mind function that I identified, I want to look at both name from the list. اللي هي مثلا تخطين الشاعر هو يدور على شاعر من هذا الشاعر. كيف نسوي جدول بناء بس بعد إنك تاخذين واحد من الأشعار ولا تلبسه وتخلينها هي سيتكس. سيتكس بداية الشعر ما يتكلم عليه. كيف تسويها في الأرض والمشكلة فعلا هو لا تسوي جميل تسوي كلمة يمد البناء على اسم الشاعر صح بس ما أظن هو البنات يعني كانوا يسوي جميل مثلا على اسم الشاعر سألنا شوي ولا لا يعني أنا مستوى الواجب يعني 5 كرسي عالية ولا إنتاج عالي ولا عادي؟
لا ممكن سمعين.
أهم شيء يعني تطبيق الألجوريثم والخطوات صحيح.
أيوة الأبروش نفسها الستراكشر يكون صحيح يطلع أوتبوت سليم خلاص. يعني زي كده سمعين يكون مرة عملية. لا لا مثلا.
تعبان ها؟ Just a little bit more خلاص. We'll have a shorter lecture and we'll go. Yeah, I'm تعبان as well. I'm actually a bit ill today. We'll finish it. Two, inshallah, we'll finish. It's very difficult, I know. I know, same for me. What can you do? Okay. Assalamu alaikum, everyone. Guys. Okay. Let's wait a couple of minutes for the other guys to show up, and then we'll start, inshallah. Okay, guys. So let's start. Okay. So let's look at the topic of KV cache. Guys, Shabab, thank you. So KV cache is an important aspect of modern large language models. It's basically one of an important area of research. So let's look at a little bit at the operational or the computational cost of large language models. So let's say you have an LLM. Okay. Let's say its context size is, let's say, 32,000. Okay. And let's say it has number of heads is maybe, let's say, 96. Okay. And let's say the dimension size of keys and values of keys and queries, I'm sorry, is, let's say, 128. Okay. Now, let's say if I ask you, I am calculating the attentions, just the attentions, okay, the attention matrix. Okay. What would be the computational cost of it? How many operations would I need? Forget about the softmax part for now. I'm talking about just the dot products of the keys and queries. I'm sorry? No, I'm not talking about the weights. So I'm talking about the operation floating point operations and calculating the dot product of keys with queries for one layer of attention. So it's a multi-headed attention. Okay, I have 96 heads. Each key and query is 128 dimension, and the context size is 32,000. So how many floating point operations would I need to calculate it? Ignore the softmax for now. Let's just focus on the dot product. Multiply all three. Okay, so let's try to do it actually and say
The key, the images, so 128 by 128 at the beginning, right?
okay, so let's do it step by step. Okay, so let's say query at time 1, and let's take its dot product with key at time 1. Okay, so this would be how many operations? Let's write this. So this would be from j equal to 1 to 128, query 1 j, key 1 j. So you will take the element wise product of keys and queries and add them up. This is the dot product, right? The dot product between key and query at one location. How many multiplications are there in this? 128. Just 128 multiplications. Okay. So for each element of this attention matrix, you need 128 floating point operations. Okay, multiplications. Okay. There are some additions as well, but multiplications are the more expensive operation. So 128. Okay. Then of course you would need it for key and query. Query at time 1 and key at time 2. Again 128. Okay. Again 128 all the way till the context size, which is 32,128. Okay. Now using this intuition, what would be the total number of operations? Okay. 128 times 32,000. Anything else? Times 32,000. Okay. And this is for a single head. Now remember, we have 96 heads. Okay. So this would be multiplied by another 96. Okay. So if I use, so this is context size square times dimension times the number of heads. So it grows with square of the context size. If you increase the context size, the number of operations grow by a square, by exponent. So if you increase the context size by 10, the number of operations would grow by 100. Okay, if you increase the context size by 100, the number of operation would grow by 10,000. Okay, this is one thing to know. Okay, this, by the way, is different from a recurrent neural network. A recurrent neural network, the operation grows linearly, because for each new token, you have to do one set of operations. Okay, here operations are going quadratically. So we have just seen good things about transformer architectures. Here is a bad thing, that is computationally expensive. Okay. Now let's look specifically at inference time. Okay, so transformer-based architectures. Yeah, let's say I'm using a language model just to create text. So I have a language model. I give it a start of sentence, and I ask it to create some text from it. Okay. So at time 1, I will have a query. Okay. At time 1, I will have a key. Okay. And my attention matrix would be Q1, K1. Okay. I will do the operation. I will produce a word. Okay. Let's say the word was the. Okay. Now this word would be fed back into the transformer. Now you have a pair of keys and queries. Okay. So this would become K2, Q2. Okay. You have two tokens now, start of sentence and the. Okay. Let's say the next word was produced day. They will come here. Now you have 3 tokens, 3 queries, 3 keys. Query 3 and key 3. Okay. And so on. Okay, as you increase, as you sample from, as you produce new tokens, you add them to the input sequence, this would become longer and longer. Okay. But the sentence that I'm producing, as I'm sampling, the sentence that I'm producing is this: start of sentence, the day, today is, and so on. Okay. I have a question for you. Let's say that I produce this at time 4. 1, 2, 3, 4, 5. Okay, I have 5 times. This is my attention matrix. I have a question for you. The question is, the query at time 1, does it need to attend to key at time 2, key at time 3, key at time 4, key at time 5? Why? Exactly, because when you are producing the first token, the other tokens do not yet exist. You can certainly not attend to them. Okay. Similarly, the query at time 2 does not need to attend to key at time 2, key at time 3, key at time 4, and so on. Similarly, the query at time 3 does not attend to the key at time 3, 4, and so on. Okay, you can build on top of it. Okay, so this is the first step. We don't need this part of the operation. This part is redundant. The next question is, let's say you are at time 5 now. Okay, at time 5, you just need to take the query at time 5 and take its dot product with the keys at time 1 to 5, collect information from it, and have the ability to produce the next word. How, by the way, do we produce the next word? Okay. If, let's say, I have the day today is, so I have the query for is, it attend to all the previous keys, and you get some output embedding for is. Okay, this is output embedding. How do we use this output embedding to produce words? Because remember, we are doing sentence completion, so we have to produce next token. But transformers just give you embeddings, right? It's doing some operations on embeddings. You have attention layers, you have fully connected layers. You have, of course, the normalization and the skip connection and so on. But eventually what you get at the end is an embedding. So what do we do on top of it? Okay, no, I have done all the attention scores, I have done all the embeddings, I have the output embedding from my transformer. The question is, using this embedding, I need to sample word. So how do I use embedding to sample word from it? So if you look at our architecture, our architecture after all the transformer layers, it has this linear layer and this softmax. This linear layer projects it into the dimension of the vocabulary, and the softmax gives you a distribution on your vocabulary. So what would happen here is that after you have done this part, you will take this embedding, you will put it into a small neural network, and this will give you a distribution. So you will get a distribution which is, it will have Friday with a probability of 0.4. It would be sunny with a probability of 0.2. It would be cold, maybe with a probability of 0.2. And it's the day today is nice with a probability of 0.2. So now you have this distribution. You have to sample from this distribution. Okay. And we can use different approaches. For beginners, I would suggest just the greedy approach. Greedy approach is you select the token which has the maximum probability assigned to it. Okay. So the next word would be Friday. Then you take the sentence, give it again, look at the output embedding of Friday, pass it through the neural network. It will give you a distribution. And maybe this time you will sample end of sentence and you will stop. This is how we generate language from transformers, from large language models. Everybody's with me? Okay, so now I'm at time 5. Okay, remember at time 5, I got all the keys, queries, values from my network. And I will have an embedding here at time 4, embedding here at time 3, embedding here at time 2, embedding here at time 1. Am I interested in these embeddings at time 5? Am I interested in these? No, at time 5, I'm not interested in it because I have to I'm talking about the output of the networks, by the way. So I have to use the final embedding and use it to sample the next word. I'm not interested in these. So at time 5, I'm only interested in the final embedding that I have at this time to sample the next word. Everybody's with me? Sure? Yeah, because this concept is important to understand the key value caching. Okay, if you are at a current time, at inference time, if you are at time t, okay, you are not interested in the output embeddings of time t minus 1, time t minus 2, time t minus 3, and so on. You're only interested in the output embedding of the final time because you will pass it through a neural network and you'll use it to sample next word. No, but that's not, so you see, the way transformer models are set up is the way we set it up is because remember we said that language is a sequential process, right? So the probability of x at time j would depend on probability of x at j minus 1 and all the way till x at time 1. Okay, this is what we assume that this neural network and softmax, it gives me this probability. Okay, so now the final output, this is giving me the probability of, in my case, when I'm at t at 5, this is giving me x at time 6, given x at time 5 to x at time 1. This one, if I put a neural network here and a softmax here, this will give me probability of x5 given x4 to x1. But remember, I've already sampled it. I've already sampled the 5th word. Okay, that's why I'm sampling the 6th word now. Okay, because you are doing things sequentially. So you started with start of sentence, the day today is. So you have sampled token 1, you have sampled token 2, you have sampled token 3, you have sampled token 4, you have sampled token 5. Now you are interested only in sampling the 6th token. So all of these previous one, these are not important for me. Okay, which means that when I am at time 5, all of these are not important for me. I don't need to recalculate them because I've already sampled these words. Okay, so now at inference time, what I want to keep is the query of the current time and the keys and values, of course, of all the previous times. That's essentially, in other words, key value caching. So what will happen is that at time 1, so let's do time 1, you will get query 1, okay, you will get key 1, and you will get value 1. Okay, at time 2, you will have query 1 and query 2, but remember query 1 is not needed anymore. Okay, remember we don't need these rows anymore. If you are at time t, you don't need queries of the previous times. Why? Because queries are used to collect information for a time state. I've already sampled the word at time 1, so I don't need to collect any information about time 1. Okay. So you can essentially drop this, but you need key 1 and key 2. Also, you need value 1 and value 2. Similarly, at time 3, you have Q1, Q2, and Q3. We don't need Q1, we don't need Q2, we just need Q3, but you need Q1, Q2, Q3, value 1, value 2. Okay, and of course, value 3. Okay, so let me show it to you graphically. Okay, so this is self-attention with key value caching. Okay. So at time 1, inference time 1, you get query 1, T1, value 1, and you get the attention score. Okay. At time 2, you just keep the query at time 2. Keys are cached. So you are caching the queries, the keys and values. Keys and values you have to store because you need them for attention. Queries you don't really care about them. Okay, so now you see at time 2, I kept the keys at time 1 and time 2. I kept the values at time 1 and time 2, but query at time 1, I don't care about it. I dropped it. At time 3, you keep the query at time 3. All the previous keys you have to keep. All the previous values you have to keep. Okay, and so on. At time 4, at time 5, and so on. The question is, why would this be a good idea? Why would I want to do that? What's wrong with the standard full attention? I can create the full attention and I can look at just the final token. It's faster, of course. Okay, because now at each time completing this, rather than completing this full matrix, you're just calculating a part of a row vector of this matrix. Okay, it's faster. So it would be somewhere of the order of n, I'm assuming. So let me quickly do the calculation. So previously we had context square, D and H. Okay, D and H would remain the same because dimension and H you're not changing. But let's see how many operations do we need to do. Previously we had C square because you had 1 to C here and 1 to C here. But now what we are doing is at time 1 we are doing just one dot product. Okay, key 1 with query 1. At time 2 we are doing 2, query 2 with key 1 and key 2. At time 3 we are doing 3, which is query 3 with key 1, key 2, key 3, and so on. So you will have 1 plus 2 plus all the way till C. Okay. And what I think I can do is I can write is C plus 1, 2 plus C minus 1, 3 plus C minus 2, and so on. So I combine these two, I combine these two, and I combine these two, and so on. Okay. If you look at these, all of these are C plus 1, right? Right? And how many of these terms you will have? Context window divided by 2. So you will have C plus 1, C divided by 2. Okay. So we are doing significantly half less computations. Okay. By the way, I did one mistake. This was a training time. At training time, we did C square plus C square DH computation. At inference time, it's not C square DH. At inference time, it's at time 1, it's 1 square DH because the context size is 1. At time 2, it's 2 square DH. At time 3, it's 3 square DH. At time C, it's C square DH. So this is significantly larger than C plus 1 by 2 DH. So we get massive speed ups. Okay, because of doing KV caching. Okay, this was the smart idea which was introduced with Llama. Okay, everybody's with me? Okay, but now, of course, everything is not straightforward in life. So there are some issues with KV cache. And the issue is that GPUs in general are incredibly fast at computation. They are not as fast as at moving memory around, at storing things and reaccessing things. And roughly speaking, A100 is computation operation are 40 times faster than memory operation. Okay, so with KV caching, we were getting too many memory operations because you are storing things and then releasing things and storing things and so on. So what becomes the bottleneck is not the computation. The bottleneck becomes the memory operations. Okay, the accessing and storing of data. This is what is the bottleneck now. So people started thinking, can we do something to remove that bottleneck? Okay, so let me write this thing. KV caching, faster in computation. However, memory operations become the bottleneck. So now the question is, can we modify our multi-head attention operation to somehow remove or decrease the number of memory operations? We want to do KV caching, but we want to do it in a way where we don't have to store so many things in memory. Any ideas, anything that you can suggest that we can use to decrease the number of memory operations in KV caching of the multi-head attention? Sorry? So context window, of course, we can play around with context window, but in general, context window would degrade the performance quite significantly. Yes, we can use this type of tricks. The trick that people started using were simpler tricks. They said like, hey, we have multiple heads, right? We have 96 heads or 10 heads or 8 heads and so on. And what we are currently doing is that for each head, we have a unique query, we have a unique key. What if we have a unique query for each head, but keys and values are shared by all the heads? Okay, that is multi-query attention. Okay, multi-query attention. The idea of multi-query attention is that, so this is head 1, head 2, and head 96. Okay, for each one of them, you have a unique query vector. Okay, so Q1, Q2, let me write it in the superscript so that we know that it's different heads. Q96, but the key is the same for all the heads. So all the heads share a key, okay, and all the heads share a value. You can decrease the heads, but remember, why did we want more heads? Because we want the ability to learn different types of relations between tokens. So if you just in a single go remove the head, then you would decrease the number of heads, you would be able to learn less things. Here we are hoping that just having multiple queries can allow you to collect different information from different tokens. Okay, this was the first attempt. Of course, the memory operations now are significantly less. Okay, you have to move 96 times less data. Previously, you had to store for each head, you have to cache a key and value. Now you don't have to do it. You just have to have, for one layer of multi-head attention, you have to have one key and one value. So this improves the performance quite a lot. Of course, we can see that the time performance would increase, but of course, output performance might decrease a little bit because you are decreasing the number of parameters, you are decreasing the learning ability of your network. So people said, hey, what if we do something in between? What if we don't go that extreme as having a unique key and value for each head, but we also don't go to the other extreme where we have one key value for all the heads? What if we are somewhere in the middle? That's where we got grouped query attention. Okay, grouped query attention, the idea is this. You have head 1, head 2, head 3, head 4, all the way till head 95 and head 96. For each one of them, you have a unique query, Q1, Q2, Q3, Q4, Q95, Q96. But keys and values are shared by heads. So in this case, let's say I do it by a factor of 2. So these two will share a key and value, Q1, V1. These two will share a key and value, Q2, V2. And these two will share a key and value, which is P48, value 40. So Llama introduced group query attention. Again, why are we trying to do group query attention? The whole point of this is that at inference time, we want the models to be fast. Okay, which means that we don't want to do too many computation of having the full attention maps at each token. Okay, we want to cache the keys and values and use the current query to find the attention at the last time t, put a neural network head on top, get a distribution on the next token, do a greedy sampling and get the next token. Okay, but when we do key value caching, we see that memory becomes the bottleneck rather than the computation. So we said, is there a way where we can decrease the number of memory operations? And the answer is yes, you can use something like grouped query attention. Okay. Okay, let me see if there is anything else that I want to show. Okay. So you see with multi-head attention, okay, we have a performance of 26.7. When you use multi-query attention, the performance drops slightly. But look here, what is the advantage? Where do we get the advantage? Can you see something between these two, which is of interest to you? So look at the times of the decoders. So from 46 seconds, the decoder inference time become 4 seconds. It's 10 times faster. Okay, and remember, the whole values of LLMs for businesses is its performance at inference time. Yeah, it should be able to give you things very quickly, and that's what we see here. Okay, let me see if there is anything else that I want to cover. I think we are good. So any questions for Llama? Okay, so Llama, what are the key architectural changes on traditional transformer? What are the changes? What are the things which are improved in Llama? Let me get a page. And so the first one is RMS normalization and move to input rather than output. Okay, so rather than doing the normalization at the output of the layers, we are doing it at the input of the layers. Okay, what else? Swig-glue. Okay, Swig-glue activation. Okay, what else? Rotary positional embeddings. And number 4, KV caching and groups multi-query attention. These are the key changes in the architecture of Llama. Okay, I have the paper of Llama as well. I just want to show you guys how these papers are written. If you want to read it, what would you have to go through? So of course, there's an introduction section. Okay, this is the first Llama 1 and 2 paper. So 3 paper, we can look at this as well. But this is basically the changes, the full talk about architecture. Okay, so let's see what do they say about architecture.
So they use pre-normalization, okay, which I just mentioned, and they use RMS norm. Okay, this is the first set of changes that we saw. Okay, then they use Swiglu activation. We saw what Swiglu activation is. They use rotary embedding, and that's it. So these papers are not terribly difficult to read. You should be able to take state-of-the-art LLM paper and read it. There isn't going to be too much difficulty for you to read it, which essentially is a good point at the end of this course. If you can read literature, I'm happy. Okay. Any questions? Yes. Yes, that's the whole point. So memory operations are typically 40 times slower on modern GPUs. So we don't want too many memory operations. We don't want too many storing and everything of data. Okay. And caching is a memory operation, right? You're storing these keys and values. So with multi-query attention, what we do is that for all the heads, we will use a single key and a single value. So the number of storage operation would decrease by a factor of number of heads. If you have 100 heads, rather than storing 100 values, you will store 100. Okay. In group query attention, the number of operations decrease by the number of elements you have in a group. If you have 8 tokens in a group, then the memory operation will divide by a factor of 8. Okay, so we want to decrease the number of memory operations to make inference faster. Any questions? Okay, so have a look at the Llama papers in your own time when you go home and see if there are any questions that you can bring tomorrow that we can look into. Okay, so what I want to do now is I want to also look at Mistral, which is another popular architecture, and see what are the changes introduced in Mistral over the standard architecture that we have. Okay, by the way, these lectures slides are from a gentleman called Omar Jamil. There's very nice content, very nice videos as well on these topics. So if you are interested in on the coding side of these algorithms, he has some very good content on this YouTube. Yeah. So let's see what is special about Mistral. What do they do, which is different from other architecture? So the first thing that they do is that architectural difference between vanilla transformer and Mistral. There are some which we would look at. Okay. Then they have something called sliding window attention. We will see what the sliding window attention is and what does it mean. We've already looked a lot at KV caching. An important part for me, which I want to show you in Mistral, is sparse mixtures of experts. Okay, this is, in my opinion, a very significant improvement on LLMs. For example, DeepSeek version 3 has a mixture of experts in it, and we'll see why it's a good idea to have this. Okay. So let's see if there are any significant architectural differences from vanilla transformer that we saw and Llama that we saw. So it seems very similar to Llama. You have an embedding, you have RMS norm, then you have rotary positional embedding. Then in attention, there is a slide chain in attention layers, because now you have sliding window attention. Okay, we'll see what the sliding window attention is. Then you have RMS norm at the output of attention layers. Here we have slightly different thing. We have a mixture of expert. Previously, we had a feed forward layer. Now you have a mixture of expert. We'll see what this mixture of expert is. And you have CLU activation layers. The CLU activation layers we have seen it's a sigmoid time the input of the sigmoid. Okay, and the rest of the architecture is fairly same. So on the architectural side, not a lot of differences. We need to look at a few things. We need to look at what is the sliding window attention is. And we also need to look at what is this mixture of experts. Two things that I'm interested in this model. Okay, let me take some pages and let me first try to introduce what is this sliding window attention. So what I will do is, to explain it, I will use the motivation from convolutional neural network. Motivation is CNMs. Okay. So if you, of course, you guys have worked with convolutional neural networks. What is the typical kernel size of convolutional neural networks? Filter size, typical filter size, 3 by 3. Okay, so images are of the size, most modern images would be about 1,000 by 1,000 size. And the filter that you are using is 3 by 3. So the question is, how does this 3 by 3 filter captures the information of an image which is 1,000 by 1,000? Yes. No, okay. So our friend is saying is that because you are doing a convolution, so this 3 by 3 filter is going to all the regions in the image, which is fine. It's going over all the regions. But how do you collect all the information from all the region into one output? You cannot look at 3 by 3 unique patches and then collect all this information together without some operation. So convolutional network, by the way, do this. They aggregate this information. But my question to you is, how do we do it? Okay. Okay. So what Mansoor is suggesting is that we can do some sort of spatial aggregation. Okay, like max pooling layers or average pooling layers and so on. I have a better idea of it. In fact, by doing stacking multiple layers, you are increasing the receptive field of the filters. Okay, let me explain. Okay, let's say I am currently working at this. Let me mark this pixel in green. At the green pixel in an image. So the first conv layer, when it's calculating the filter output at this green pixel, it would look at a 3 by 3 region, right? So it will give me this output. So at this green pixel, I'm looking at this 3 by 3 patch. Now let me look at this blue pixel. When I'm looking at this blue pixel, I'm looking at this 3 by 3 patch, right? Which is the blue pixel here. When I'm looking at this purple pixel, I'm looking at this 3 by 3 patch. Okay, give me the output at this purple pixel. I'm not going to do all 8 pixel. I'm just going to do the corner pixel just to convey the point. Okay. When I look at, take another color, black. When I look at this pixel, it's looking at this 3 by 3 patch. And finally, when I'm looking at, let's say this pixel, it's looking at this 3 by 3 patch. This is the output of the first layer. Now let me look at the output of the second layer. Second layer, I'm interested in finding convolution at this green pixel. So I'm looking at this 3 by 3 patch. Okay. And the output, of course, would collect information from this 3 by 3 patch. But let's see where this blue pixel is collecting its information from. It's collecting its information from this region. Okay. The purple pixel is calculating its information from this region. So essentially, what you're doing is that for the black pixel, you are collecting information from here. For the orange pixel, you are collecting the information from here. So this 3 by 3 region is essentially collecting the information from 5 by 5 region. And as you go deeper and deeper in the network, you are looking at bigger and bigger. And this is called receptive field. Okay. So for the deeper layers, the receptive field is bigger. The idea that I want to pose to you is, can I do something like this in attention? Okay. 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 So what I would do is I would say that I would use a context window of 32. but I'm going to use a sliding of 32,000, but I'm going to use a sliding window attention. So let me explain what I'm trying to say. I'm going to say that when I'm trying to find the embedding, the output embedding for a word, let me write a sentence. Let's say, yes, let's use the same sentence that we have been working on. Start of sentence. The day today is. Okay. I'm going to say that my context window is, let's say, 1, 2, 3, 4, 5. Context window is 5. Okay. But the attention window is 2. Okay. So each word can attend to the previous 2 words. Okay. In fact, let me say the context window is 2, so it can attend to itself and 1 previous word. Okay. So at the first layer of attention, this can only attend to today. Right? Okay. So this is the first layer of attention. Attention, layer 1. Okay. So you get an embedding for is. You get an embedding for is, an embedding for today, an embedding for layer, an embedding for an embedding for start of sentence. Okay. So the embedding for is looking at is and today. What is the embedding for today looking at? Embedding for today is looking at today and day. Okay. So now in the second layer, okay, again, attention is 2. Okay. So this embedding, the embedding for is can look at embedding for today. But remember, embedding for today has already looked at day. So in the second layer, your receptive field has become 3. And the third layer, the receptive field would become 4. Fifth layer, receptive field would become 5. So now you are doing attention in this full context size, but you are using a window for it. You're only looking at 1 previous word or 2 previous word or 3 previous words. Okay. You still manage to look at the full context because you have multiple layers. You don't have just 1 or 2 layers. You have 96 or 100 or 200 layers. So you would look at the full context, but the information would be collected in a gradual manner. You don't, at each step, you don't need to look at the full image at each, or full sentence in each attention layer. First layer, you look at a part of sentence. Next layer, you look at a slightly bigger part of the sentence. Next layer, you look at slightly bigger part of the sentence, and so on. Okay. Now, my question to you is, why would this be a good idea? Yes, at training time, you would have slightly lesser number of computation, but training time is not super important because remember, even when we had the full context window, we did not have many issues at training time. We were doing things very fast. Okay, so the key importance of this, the key advantage of this is at test time. Okay, at test time, so you see what did we need to do at inference time? What did we need to do? We need to store the keys and values. We need to cache it. Okay, we need to cache it in the size of the context window. But now if I'm using a sliding window of 2, I just need to store the previous 2 keys and values. I don't need to store other keys and values at each layer. You see the point? That's basically the full idea. Okay? It allows you a mechanism to be significantly faster at inference time. Okay, everybody is with me? So a question for you is, when I'm doing training, how would I implement this change? So remember, in training, we were doing the Q1, Q2, Q3, Q4, Q5. These were the queries. And K1, K2, K3, K4, and K5. We had a dot product of it. Okay. And this was our attention map. Okay. The first thing that I will ask is that we managed to do a causal map. We found a way in training to prevent our query from looking in the future. How did we do it? Masking. And we masked it with what? Negative infinity, right? So what we did was we said that this part, this was negative infinity. I'm sorry. We masked it with negative infinity so that you take softmax, you'll get 0. So a query would not be able to look at the future. It will only be able to look at the past. Now I want you to implement a sliding window as well, which is I want you to prevent a query from looking at more than 2 words behind. A query can look at itself and it can look at the previous word. It cannot look at other previous words. How would I do that? Okay, that's exactly what we would do, but how? Which part should I mask? Let's say I have a sliding window of 2. I'm looking at the word and the previous word. But which part should I mask? Okay. For Q1, it's the same. For Q2, it's the same. What about Q3? Okay. Exactly. What about Q4? What about Q5? That's it. So now at the training time, implementing sliding window attention is very simple. You just need to do masking. Okay. Just simple masking. And now your attention is a sliding window attention. Okay. So now you are at each layer, you're only looking at a certain window size to learn. Remember, the context is not decreased. You're still looking at the full sentence, 32,000. But in each layer, you are looking at small chunk. So think of it this convolutional example. You're still looking at the full image. But at each layer, you are looking at small receptive field of this image. Okay. So it's a very smart, decent idea. Okay. How will it improve things at inference time? So what is the improvement at inference time? Okay, let's do it step by step. Let's say at time 1, you will have query 1, you have key 1, you have value 1. Okay. At time 2, you don't need to store Q1. Okay. So you will have Q2, you will have key 1, key 2, and value 1, value 2. At time 3, you will have Q3. Now K1, you can overwrite it. Okay, so you will write it with K3 and K2, V3 and V2. Okay, at time 4, you have Q4 and you have K3, K4, V3, V4. That's the advantage of sliding window attention. Now you have to store less amount of information at inference time, which means memory operations are fewer, which means you would be faster. You would be at inference time, you would be faster. Everybody is with me? So what they would do is they would do some ablation studies. So you would use the same data, traditional architecture and their architecture, and do both. For example, I just show you they had a comparison between multi-headed attention and multi-query attention. They would use everything the same. They will just change this one thing in the network and show you that, okay, it performs better. Okay, so that's basically the idea, that ablation studies are a must. You need to see this thing. The claim is not that its performance is better. The claim is that it's faster at inference time, which you can test. It's independent of the training and everything. You can produce random tokens from it. If it's producing faster, then your job is done. Of course, you don't want the quality to degrade, but the quality, if it's matching the previous quality and you are faster, khalas, your job is done. Okay. Now, the next step which is remaining is the mixture of experts. I'm sorry? It's more than one neural network, yes. But there is a smart idea for it. Yeah. Okay. Okay. So what our friend is asking is that we said that we are collecting some information in the first layer, not head. Okay, first layer of attention, second layer of attention, third layer of attention. What is that information? What are we learning? Okay, am I saying head is in the same layer? So you have two things. You have layers and you have heads. Okay, so heads is basically you have a layer of attention. Let's say this is layer one. A layer one would have multiple heads. Okay, so you will have a query one, okay, but for head one, a query two for head, a query one, I'm sorry, for head two, a query one for head three, a query one for head four, a query one for head five. Think of it like this. So you have a sentence. Let's say the day today is, and so on. You are writing the sentence. So the query for this can ask multiple questions. So for example, a query can be, hey, are we talking about birthdays? This is a query. This is a question that this token wants to ask. Okay, but of course, this might not be the only question that it wants to ask. It might want to ask a question. Are we talking about National Day? Are we talking about weekdays? And so on. So query, remember, is asking a question, right? I want an attention layer to have the ability to ask multiple types of questions. Each head would ask a different question. That's the purpose of different heads. Okay, I don't define what question it should ask. It's learned. It would learn it from all the data on the internet to see like, hey, the early layers need to ask this type of question. The next layer needs to ask this type of question. The next layer needs to ask this type of questions and so on. But it's learned. Window size 2. Yeah.
You said at the beginning, we implement. Now,
Yes.
the next step will be.
Yeah, but this is next layer. It's not next head. It's next layer. All the heads are in a single layer. Okay, what you are saying is next layers. So the question is, you have a sentence, let's say the day today is. The question is, how do we have this hierarchy of information across different layers? Okay, so remember, let's again take the example of day. Day, this is layer one. Okay. Layer one will have multiple heads, multiple queries. This would try to collect some information about the day in its neighborhood. But remember, the neighborhood size is just 2 now. So it can just talk to the, okay, whatever information it can collect from the. Okay, it will ask this question, collect the information from the. This information now would be stored in the output embedding of this token. Now you have second layer. Layer 2. Okay, again, you would have multiple queries for day. Now this will ask information again from its neighbors. Again, it's the embedding of the, but embedding of thou now has collecting information from the previous tokens as well. Why? Because you are in second layer. So as they collected information from the collected information from the previous word of the, which is maybe it's an essay about Saudi National Day. Okay, So now you will have information from 3 tokens, the token itself, the previous token, and the token before it. As you go to the next layer, again, you would repeat it. So now you'll have information from the current token, the previous token, the previous token, and the previous token. Another layer, so on and so on. The question that you're asking is, how do I know that this happens? This happens because when I'm, let's say, at layer 4, I'm looking at the word itself and the previous word. Okay, this is the thing that I'm looking at. Okay. The information for the word itself comes from the previous 2 tokens from the previous layer. And the information from this comes from the previous 2 token. So now in the previous layer, I'm looking at the 3 token. The layer before that, the information for this token came from previous 2 tokens. The information from this token came from previous 2 token. And the information for this token came from previous 2 token. So I'm looking at 4 tokens in a layer below. Again, information came from previous 2 tokens, from previous 2 tokens, from previous 2 tokens from. So I'm looking at each layer that I go back in the network, I'm looking at bigger and bigger windows. That's how it's achieved in sliding window attention. Everybody's with me? Okay, so coming again to mixture of experts. Yes.
So, showing along of layers, each layer will look at, I will add another, I will add one word that will look at. So there's no fixed number of layers that we can deal with, because the sentence, we don't really know what the length of the sentence is. So how can we?
That's a good question. So what I would recommend is that, for example, I know the context window. My context window is, let's say, 32,000. Okay. So if my context window is 32,000, okay, and let's say the number of heads I have is 100. Okay. So what I would do is 32,000 divided by 100. My sliding window should be at least 320. Because if it's not 320, I cannot look at the full context. So I would at least have more than 320 elements in my sliding window. If I have, then I can look at the full context. Okay, this is how we will design it. This is a design choice. We would look at a few things and we would, so maybe something like around 500 would be a good number. 500 you would be able to look at. 500 you would be able to look at all the words in the context when you go through the full transformer network. Yeah, everybody's with me? Okay. So let's look at the mixture of experts. Mixture of experts. So far what we have seen is our transformer architectures are this. You have some input embedding. Okay. You have some, I'm removing the positional embedding and the normalization. I'm just talking about core layers. Okay. You have attention layers. Okay. Multi-head attention layers. And then you have some fully connected layers or feed-forward network. Okay. This is our architecture. Now, if you look at it, our language models, they are kind of now foundation models. They can be used for multiple things. They can be used for summarization. They can be used for question answering. They can be used for writing poetry. They can be used for many things. Okay. Now this architecture, and of course this is repeated certain number of times. For example, in GPT-3, it's repeated 96. We have 96 layers of attention, 96 layers of feed-forward network. But it's a very hard constraint. You have a fixed architecture to do all these unique tasks. Question answering in different contexts. Question answering in math, question answering in chemistry, question answering in physics, and so on. Translation, let's say text completion, summarization, and so on. My question to you is, can I somehow have different parts of the network learn different tasks. Can I have a part of this network which learns, let's say, question answering, which is an expert in question answering? Can I ask a part of this network to be expert in mathematics? Can I ask a part of this network to be expert in logic? And of course, I don't know these areas beforehand. So I cannot say, hey, you be expert of this, you be expert of this. This has to be learned. This has to be flexibly learned from the data. That's my question to you. Can I somehow have the ability to flexibly learn different concepts in this network? Okay, I'm going to make the problem simple. I want to modify the feed-forward network, the fully connected part of this network, such that I have the ability to flexibly learn different tasks.
Maybe know the task. We have it's some path.
Yes, that's exactly the idea. Okay, so what if we can activate certain paths for certain tasks? Okay, so what I will do is I will say that I will have slightly different from it, but yes. Okay, so what we will do is we will have an attention layer, but then following the attention layer, we don't have one feed-forward network, we have many. Okay, in the case of Mistral, it's 8. So you have 8 feed-forward network. Call it 1. Okay, and what I want to do is I want there to be a flexible mechanism of activating different feed-forward network. For example, if I'm doing language translation, I would go from attention to, let's say, the first feed-forward network. Mistral had a design choice of using 2 experts for each task. Okay, so maybe I go for the first and third one. Okay, let's say I have a task of question answering. I go for first one and second one. Let's say I have a task of, I don't know, poetry. I go to 8th one and 3rd one. So I want to have this mechanism. This is called sparse mixture of experts. Sparse because you're only selecting 2 out of the 8 experts. So the question is, how can we do it? Remember, I want to do it through a mechanism through which I can back propagate. Okay, because of course I want to train it. I don't want to just say like, hey, you be expert for English, you be expert for this. No, all of this has to be trained. So I'll make the problem slightly simpler for you. Once we do the attention layer, what is the output of the attention layer? Output of the attention layer is embedding, right? You have some embedding dimension. Let's say we are talking about GPT-3. So we have 12,228 dimensional embedding. Okay. Now, based on this embedding, I want to create some gates. Okay. I want to have a function where I have some gates with which I can activate certain experts. Okay. So this is gate 1, gate 2, gate 3, all the way till gate 8. Okay. I want to have the ability to activate these gates. How would I do that? I'm sorry. Okay. So first thing is that how do I convert this 12,228 dimensional vector into an 8-dimensional vector because I have 8 gates? Projection, you just do a linear transformation. So you have a linear layer which takes in W of embedding plus B, and this gives you gate. Gate is 8-dimensional. Okay. The next thing that we do is we take the 2 highest entries of this gate output. Okay, 2 highest real numbers. Okay. So let's say gate 1 and gate 5 has the highest value. I take the softmax of these 2. This basically would say that, let's say the softmax output is 0.8 and 0.2. So it would say that after this attention layer, go to feed forward network 1, take its output, multiply it with 0.8, go to feed forward network 5, take its output, multiply it with 0.2 and add it. Okay. So based on the value of them, essentially, see, what does embedding have? Embedding has the information of the task that you're trying to do because it's looking at the context, it's looking at the prompt. Okay. So let's say if the embedding tells the mixture of expert part of the network that it's a sentence completion task. Okay. So the linear layer would activate the gates, which open the experts, which are experts in sentence completion. So it would say, go to expert 1 and expert 5. So think of it like this, like you guys are experts in different things, and we get people with different requests. Some of you are Jawazat, some of you are MOI and so on. I am the gate. So a person comes to me and he says like, hey, I have an issue with Jawazat. I say, okay, Jawazat, go to counter 3. Yeah. Another person comes and says, I have an issue with traffic. Say, go to counter 5. That's exactly what mixture of experts is doing. Okay. But we are doing it in a learned manner. We're not fixing this. Okay. And this is essentially a very smart idea because you don't overload the fully connected layers with all the tasks. You have multiple experts, different experts can learn different tasks. And then you can activate different experts with different tasks. So it's the example of this would be that rather than each one of you learning all the tasks of MOI, different people are learning different tasks. You are experts in different things, and then we are transferring the right problem to you guys. And this is a fairly strong tool. As I mentioned that DeepSeek 3, for example, also use a mixture of experts with 8 experts and so on. Okay. Let me show you a graphical visualization of this. Okay. So this is basically the a graphical visualization of the mixture of experts. So essentially, you will get some input embedding. It would pass through a fully connected layer, and you would look at the 2 highest values. So in this case, the highest value is 1.5 and 1.2. Okay, 1.5 and 3.4. You take a softmax of these and take the output of these two, weighted by the output of the sigmoid, add them up, and that's the output of this layer. No, it's quality. Okay, time-wise, it's same. Essentially, you are for each operation through each. Well, it would be slightly slower because you are having 2 experts rather than 1. But in terms of quality, it would be quite good because see, what is the core idea? The core idea is that I want to, rather than my fully feed-forward network learning all the tasks, I want different experts to learn different tasks. So think of it like this. For example, this might be expert in English. Okay, this might be expert in math. Okay, this might be expert in Arabic. So if you want to do English to Arabic translation, you will activate expert 1 and expert 3. Right? Because that's the task that you want to do. You want to do translation from between the 2 languages. If you want to do math problem and the problem is in English, you will activate expert 1 and expert 2 because you are trying to do math and the question is in English. If you are trying to solve math problem, but the question is in Arabic, you will activate gate 3 and gate 2. Okay, so that's the idea. So we train it end to end. Okay, we don't specify. I don't say that expert 1 has to be an expert in English. I don't say expert 2 has to be an expert in French. I just train it end to end. I have to check whether they fine tune it end to end. I have a feeling that they might fine tune it end to end with something like LoRa. Yes. Okay. So if, for example, certain experts are, let's say, unimportant for a task, the weights of the perturbation that you do for the weights might be very small. But I have to check. I have to check what is the right way of fine tuning mixture of experts models. Okay.
Is the size of
I'm sorry, what multiplied by what?
it 5 by 16.
Okay.
What is the size?
Yeah. So this is size of the network, but it's saying that it has 8 experts. 7 billion parameters, but it's a mixture of 8 experts.
It's not quite what we don't do.
Mixture is not very popular, but like I said, mixture of expert is popular because it's not in DeepSeek version 3 as well. Okay, and mixture of expert in general seems a very decent idea. I don't have a very solid intuition of like whether it would be easier to train or not very easy to train because you have lots of paths for gradient to flow. I have to read up a little bit on that. But in terms of core idea for solving the language modeling problem, it's an excellent idea. Hmm. Hmm. Hmm.
Very good.
Yeah, I'm quite sure, but I'm telling you, like the very best, like DeepSeek, is a mixture of experts. So, so if I have to choose between Alam and DeepSeek version 3, I'll certainly go for DeepSeek version 3. Okay. The only issue that I'm telling you that I can foresee is stability in training, because there are multiple paths. You have some gating, you have manual selection of 2 gates. There might be a little bit of some trick there, but I have to look at their paper and see if they mentioned anything in this in detail. Okay. In fact, let's look at the paper together and see if we can find anything in there. Okay, so this is their paper. Okay, let's see what are the key concepts. So architectural detail. So sliding window attention we have seen. Rolling buffer is basically at inference time. Remember, I was overwriting the keys and values. This is rolling buffer. Prefill and chunking. This is just some computational thing. We didn't cover it in detail, but I think it's fine. Other than that, I don't see any problem. Again, go home, have a look at it. These are small papers, 5 pages, 6 pages paper. Have a look at it, see if you can bring any questions, and we would look at them in details. Okay. But at the very least, I'm happy that we are at a stage where we can look at any literature of large language model, NLP state-of-the-art literature, and we can read it. Because if you can read papers, then you don't need me. You are experts. You just read papers and read codes. 2 things, then you are good. The only part which I have a feeling that we might need to work a little bit on is the reinforcement learning with human feedback. So I'll give you one example. Let's say that I go to DeepSeek version 3. Okay, and okay, this part I'm quite sure we don't fully understand yet. Okay, and this is what you will see in large language model papers, is that it would be all English. Okay, no math, except for reinforcement learning part, which would have something like this. Some very tricky looking expressions, and these are indeed quite tricky. But we will look into it. We will look into it. I will give you guys at least, inshallah, enough intuition for you guys to be able to read it and understand it as to what is going on inside these models. It's about 50 years of reinforcement learning knowledge that we have to compress in 2 lectures, but we'll do it. By the way, 2 of the main characters in reinforcement learning, Sutton and I'm forgetting the other guy, they recently won the Turing Prize for their work in reinforcement learning. So Turing Prize is the highest prize in computer science. It's like the Nobel Prize of computer science. So and I think a significant amount of publicity to the field of reinforcement learning came with large language models. I will just motivate a little bit. I'll take 5 minutes. I'm sorry, usually we have a break around 2. I'll take 5 minutes and we will finish 10 minutes early. Okay. So the core idea of reinforcement learning is this. reinforcement learning with human feedback. Okay, so the issue is that if I train a language model with data on the internet, it's typically not going to be very well behaved. In fact, there are some nice examples. So it's slightly old story, maybe like 6-7 years old. Microsoft produced a chatbot, and they called it Tay. Okay, you can Google it and you'll find the story. So they created it in 2 languages, one in English and one in Chinese. And the idea was that you talk to the chatbot and it learns. Yeah, it learns from conversation that people have with it. So the English-speaking world is English-speaking world, and they were like saying racist things to the chatbot and sexist things to the chatbot, and the chatbot became like a Nazi and very quickly. So Microsoft had to close it, to shut it down. The Chinese version, because people are having nicer conversation with it, it stayed up and it's very easy. This is the issue with using raw data from the internet, is that it would not be something that you would want to put under your company name in public. So the question is, can we take these large language models and align them with what we want them to do? Alignment is basically modifying the behavior of large language models to certain guidelines that we as humans fix for them. Okay. For example, I don't want a language model to be overly political. I want the language model to be neutral in political discussions. And you can see that normal chatbots that you have available, if you ask them to render an opinion on political matters, they would be fairly neutral. Okay. So the question is, can we do that? The answer, at least I can think of 2 ways of doing it. One is with supervised fine tuning, that you just get high quality data and just give it the high quality data and say like, just produce this. Yeah, this is one approach. The other approach is the reinforcement learning approach. Reinforcement learning approach essentially is that for every action, there is a reward. Okay. If the action is good, you get a high reward. If the action is bad, you get a low reward. And the idea is to have models produce actions of high rewards. Okay. I will set up the full theory of reinforcement, but that's what we want to do. And typically, reinforcement learning are quite solid tool for aligning network. Okay. So starting from the original GPT paper, they use a proximal policy optimization, PPO algorithm. Then we had DPO algorithm, direct policy optimization. And now in paper like DeepSeek version 3, we have group relative policy optimization. These are reinforcement learning algorithms. And essentially, it tells them, it gives network some outputs which are good, some outputs which are bad, label. Then we tell them like, hey, adjust yourself, align yourself to produce output like the good ones and not produce output like the bad one. Remember, supervised fine tuning is brilliant, but the only issue is it's telling the network what to do. It's not telling the network what not to do. Okay. Of course, you can say by telling it what to do, it's implied what not to do, but the implied space is very large. Okay. So it's good to explicitly tell the network not to do certain things. That's where reinforcement learning comes in. Okay. And we would look at it, inshallah, in detail tomorrow. Okay. Any questions? Okay. I'm sorry, we will finish slightly early today. I have a bit slight flu-like symptoms today, and I want to sleep it off. Inshallah, tomorrow I'll be better. But if not, still we'll go through the normal routine. Okay. So we'll look at, inshallah, I'll try to wrap up much of reinforcement learning tomorrow and maybe early part of the day, and then last part of the last day we will do a broader overview of what we did in the course. I'll try to do some sort of summary of DeepSeek version 3 as well. This is the state of the art these days, so we'll just see what are the major improvements that they have. Okay. Any questions, guys? Shabab, Banat. Okay, no questions. So let's end the session here today, inshallah. I'll see you guys tomorrow. So.
شباب في ناس موجهين اثنين غير الدولي. كمان اليوم بعد رمضان والاتحاد فايز